In this video we're going to look at the preparation of aldehydes and ketones and their oxidation as well. So for the preparation, what we're just going to do is refer you back to your alcohols notes where you can look at how aldehydes and ketones can be prepared by oxidation of alcohols. Remembering that primary alcohols can be oxidized to aldehydes and that secondary alcohols can be oxidized to ketones. And remembering that the oxidizing reagent for that is acidified potassium dichromate, and that the conditions are different depending on whether you want to achieve an aldehyde or a ketone. Now we're just going to have a look at the oxidation of aldehydes. Again, you looked at this in the alcohols pack. Aldehydes are readily oxidized to carboxylic acids. So remembering that an aldehyde has the structure RCHO and a carboxylic acid has the structure RCOOH. And that oxidation is increasing the number of carbon-oxygen bonds while decreasing the number of carbon-hydrogen bonds. We're going to be losing this carbon-hydrogen bond here, the bond to this hydrogen, in order to gain a bond to an oxygen. Okay, so we're going to increase the number of carbon-oxygen bonds while decreasing the number of carbon-hydrogen bonds. So there's a number of different ways that you can achieve this oxidation, a number of different oxidizing agents available to us. So the first thing that we could do is we could reflux our aldehyde with acidified potassium dichromate. Now acidified potassium dichromate has the formula K2, that's the potassium, and the Cr2O7, that's the dichromate ion. And the acid we use is dilute sulfuric acid, so acidified potassium dichromate. And what you'll see in that is because potassium dichromate is orange, and when it causes oxidation, it itself undergoes reduction, the solution is going to turn from orange to green. So the solution is going to go from orange to green. The next reagent that you could use, and this is actually a test, so if you look back in your organic analysis pack, you can look at the tests. You could warm in a water bath your aldehyde with Tollen's reagent. Remembering that Tollen's reagent is a complex of ammoniacal silver nitrate, so it's got silver ions in there. Sorry, I've just correct that there. Tollen's reagent. So we've got some silver ions, and what you're going to see is if the silver ions are reduced because the aldehyde is oxidized, you'll see a silver mirror form on the outside of the test tube. So warming with Tollen's reagent. And then the final one that we have is we could warm again in a water bath with Fehling's solution. And Fehling's solution contains copper ions, copper 2 ions, and when they cause the oxidation of the aldehyde, they themselves are reduced. So the solution gives a brick red precipitate of copper 1 oxide. We get a brick red precipitate. That's just a little reminder there that those last two, Tollen's reagent and Fehling's solution, are functional group tests that allow us to tell the difference between aldehydes and ketones, because ketones cannot be oxidized. There are no hydrogens on the functional group carbon that can be removed, and therefore they cannot be oxidized with Tollen's or Fehling's. Tollen's reagent contains this complex ion of ammoniacal silver, so it's still an ion, it's still got a charge, and when you warm it with your aldehyde, you're going to see our silver mirror. This is because the aldehyde is being oxidized to a carboxylic acid. Meanwhile, the silver ions are being reduced to silver metal. So we're getting some solid silver metal forming. So if we look at these equations, we can see that if we take our aldehyde with our CHO group and we oxidizing it using our oxidizing agent, we use O in square brackets to represent an oxidizing agent in organic chemistry balanced equations, we can make a carboxylic acid. Meanwhile, the Tollens reagent, the ammoniacal silver, is picking up an electron, it's being reduced. While the aldehyde is oxidised, the oxidising agent is reduced to make solid silver metal and some ammonia. Similarly, failing solution is made from a mixture of solutions and contains copper 2 ions, which are blue in colour. And when an aldehyde is warmed with failing solution, a brick red precipitate is seen, and this is because the aldehyde is oxidised to a carboxylic acid, just like above, so it's exactly the same equation as when Tollens oxidised it, and the copper 2 ions are reduced to copper 1. That Roman numerals refers to the oxidation state of the copper, so the copper has been reduced from 2 to 1 oxide. Now if we try to write a formula for that, since it's copper 1, we know that we will need 2 coppers to balance the oxide ion. Copper 1 oxide, Cu2O.